All right, let's. So we will be talking about trig a little bit today. Before I get started, I thought it's Halloween today, so I thought I'd share.
Wait, this is my favorite comic.
I thought I'd share a Halloween-inspired foxtrot. Foxtrot is supremely great. It's also nerdy, and many times it's nerdy, which makes it an attractive cartoon in my mind. Comic. So can you read it from where you are, or do you need to read it to you? Can you read it? Go ahead. Tonight you can say that. Yeah?
One day, 10 chapters in one day.
It's not like funny, haha, but it's like, it's cute, alright? So tonight you can say trick or treat when you go to the door and threaten them with trigonometry. Now, we're not gonna step all the way into trig today necessarily, but we do want to like start talking about angles, and their measure is actually the title of today's lesson. But before we do that, we are starting a new unit today. Did you know that?
We took a unit test.
We took a unit test on Friday. That's right. So I thought I have a couple warm-ups for the next 2 days here. So I was down in Leesburg. This is actually a couple of years ago now. And I don't know about you, but I'm the kind of person who, well, you don't drive yet, but I'm the kind of person who like waits till the gas light comes on to fill up. That's how I roll.
Living on the edge, right?
Yeah, I like to live on the edge a little bit, or I'm lazy, one of those things. So anyway, I didn't plan to have to stop here, and it was, I don't know where this, I still probably couldn't get you back there today. Like, yeah, they might have changed the sign by now, I would think. This was a number of years ago. But I was just amazed that somewhere like unrelated, down in Leesburg, Virginia, I was like, what? This sign? For real. For real. This sign, their placard said, Unit 4, trigonometric functions. I was, just like you are right now, just jaw-dropped, dumbfounded. Are you, excuse me, are you casting seeds of doubt? How dare you?
It's Halloween. It's a cloud of doubt and confusion.
All right. So the goal today is to talk about radians a little bit and actually like rekindle our love for them. Degrees, minutes, and seconds. We'll talk about those measurements of angles as well. And we'd also like to talk about calculating arc length and talking about the relationship between linear speed and something called angular speed. So we're gonna. Those are all of our goals for today. We'll see how we do. Now, before I actually remind you how to measure an angle in radians and say what radians are, I'd love for you to tell me. How do we measure an angle in radians? Well, give me like I come across an angle in the wild. Okay. I'll draw a picture. Okay. I come across an angle in the wild. Listen, guys. I would like instructions from someone on how to like measure the angle I found in the wild in radians. Like, how do I do that? Like, give me an easy 4-step process or something. Yeah. Jasper has a first step for us, maybe. What do you want to talk about?
Well, an entire circle is...
Listen.
Entire circle is 2 pi.
Oh wait, I don't see a circle. So let's call step 1, at least according to Jasper, let's draw a circle. Can we do that? Huh?
You have to tame it. You have to make sure it's not going to like bite you.
Thank you, Katie. You're right. Step 1, tame the angle. All right. Once it's tamed, then draw a circle. Where would you like to center the circle? Yeah, at the vertex of the angle, maybe. Listen, guys. I know this is wild. Okay. And then what would you like the radius to be too, Jasper? I'm asking you questions. What would you like the radius to be? You don't care? All right, I picked 5 feet. All right, so I say 5 feet is the radius. All right. So Jasper says step 1, tape. Step 2, draw a circle. And of any radius you like, he said it didn't matter, so I picked 5 feet. Centered at the vertex of the angle. Someone suggests step 3. Then what? Look at what? Someone say something. Where are you?
Something.
Robin. Sub-tens, I think, is like the fancy geometry word. Yeah, but yeah, this arc here, you want to measure it? You measured it probably, didn't you already? I can see. This measured 5 feet. What do you think that measured? What do you think? Name, put a number on it. What? 0.6 feet. Okay, well, I mean, but how about you pick a nice number just for everyone's minds here? 2? Okay, 2 feet. All right, so let's say it's 2 feet. And by that, she means this distance she measured to be 2 feet. How'd you do that, by the way? It's a curve. Okay. Sufficient answer. All right, next step. Gee, what'd you say, Cassie? Oh, that's a beautiful idea. I actually have. Oh, there you go, a measuring tape. This is what a great visual. It's wonderful. Excuse me, what if she comes across an angle in the wild? She's ready? Well, I don't understand. All right. Then what? Step 4. Someone help me out. Preheat your oven to 350 degrees. No, what's step 4? I like where this is going, by the way. I'll just say that. We still would like, what are we trying to do? We're trying to measure the angle in radians. Wait, hey, guys. I want to have a big conversation here. Someone suggest anything, even if it doesn't seem helpful. Just suggest something. Yeah, right.
You could measure the radius.
It's.
If you've already measured the radius.
We have. It's 5 feet.
Then, oh, I forgot that. I knew that. See how many times the radius can fit into that little arc that you have measured.
Okay. I have. Yeah. How many times does 5 fit into 2? Is that what you're saying?
Wait, no. See how many times the radius. Wait. No, I already know how many times the radius can go around the circumference of the circle because that's the formula for the circumference of the circle.
I actually really love what you said. I just don't think you even understand what you said completely. But actually, you're right. You're right on. But say. Go ahead, Grant. Find the circumference. We can do that if you like. What is it? Yeah, it's 10 pi. Okay, got it. There's the circumference. 2 over that? Is this it? Okay, so that's like I'm with you. That's the proportion of the circle that arc represents, or something. Okay. We're trying to get the radian measure that angle. Multiply by 2 pi. Can you tell me what you get? Are you with him on this a little bit? He happens to know that there are 2 pi radians in a full circle or something. I don't know how he knows that, but he knows that. What'd you get? You got 2/5? Do you think there's maybe? I think that is actually correct. But is there maybe an easier step 4 instruction that you could give in 1 breath rather than 7 breaths? Yeah.
Divide the arc by the radius.
Oh.
That's what I said before.
Say it again. That was profound, Crystal. Say it one more time. Divide the arc by the radius. Done. Yeah, now, Bryn said it actually earlier. She just didn't even know what she said. She said, how many times does she said, how many times, like, how many radiuses fit in this distance, right?
And then everyone was like, no, that's not right.
No, I don't know if anyone understands what I mean, because your first instinct is like 5 doesn't fit into 2. Like, how many times does 5? Oh, wait, if I ask how many times does 5 go into 2, I think the answer is 2/5. Isn't that how many times does 5 go into 2? Yeah, so she was right, actually. 2/5 is the radian measure of that angle. And I want you to stop and appreciate the fact that, actually, that's a beautiful way to measure an angle, isn't it? Because all you have to do is take 2 measurements and divide. You could, like, have a discussion about this with an alien on another planet, and they would be, like, right there with you. Well, okay, whatever. Measure the arc length, measure the radius, divide. But if you were to tell them how to measure that arc length, measure the angle measure in degrees, you would first have to tell them about the history of Earth. You'd have to say, okay, well, where I come from, we have this thing called like degrees that we like thought about, and we have 360 of them. We declared that to be true. That there are like 360 of them in the circle, and that has to do with the fact that like our planet goes around, has approximately 360 days in a year, and like this old in Samaria there was like this, and you have to like back then they like decided that this would be a good measurement for. You have to like go through like the history of Earth in order to like teach them about degrees, right? Feel like why that makes sense. But here this is very natural to just be like, this is how we measure an angle. So that's what a radian is. It's just the radian measure of angle is the arc length divided by radius, which is very, very intuitive and natural. Here's the picture of 1 radian, right? Obviously, if we only open it, if the distance you measure around the arc happens to be 5 feet on that circle, well then of course you get 1 is the answer, not 2/5. And that would be of course 1 radian. Well, there's the picture. We call that 1 radian. And of course, if you were to go, a radius along the edge of your circle, and then another radius, that'd be 3 radians. You would be almost at a straight line, right? We're going the opposite direction, but not quite, right? It just so happens to be that it actually takes a little more than 3 of those to get around half the way around the circle, right? Approximately 3.14. You might have heard of that number before. You're gonna like this picture here too. There's us doing this. I stole this from somewhere. See? 3 and then a little more. And then how about pi more of those to get the whole circle? I just want to make sure you're clear, because another thing that another thing I think that some of you think of is like, oh, before we ever start this discussion, I know there are 2 pi radians in a circle. Well, wait, that's putting the cart before the horse a little bit, isn't it? Let's start with the definition of radians, and then as a consequence of that, afterward, we discover maybe that, oh, there are 2 pi of them in a circle, right? So, do you like this picture? Isn't that fun? Is it life-changing? All right. All right. Now I need to talk about degrees a little bit. Finally, it's not like we're totally hating on degrees. People still use them, so we still have to be able to talk to Earth length without this stuff. Okay. So, if you want to be more precise, sometimes people talk about something smaller than degrees too. They use degrees, minutes, and seconds to record the measure of an angle. I know it's a little bit weird that it's measured. They're calling it the same thing as what we use for time. But minutes, it does actually kind of help us remember how this is measured. Again, thank the base 60 folks of the past for this. There are 60 minutes in a degree, and 60 seconds in a minute. So that's easy to remember then. But we do have to remember that we're actually not at all talking about time. This all has to do with the Sumerians and clocks and the nature of Earth and the divisibility of 60. They like base 60 a lot. I mean, base 60 is actually pretty attractive. It's got lots of properties. Yeah, you can count the bases on your hand. Yeah. Let's do some unit conversion, everybody. Robin has a question though.
Oh, wait. Never mind.
So if someone just says, here it is in pure degrees, what is it in degrees, minutes, seconds, right? So clearly the whole number of degrees is 37 degrees plus like almost half another degree. What is that piece, that partial degree, what is that measured in minutes? What would that be in minutes? Well, how do we convert just this piece here to minutes? You guys should be good at conversion factors here. Yes, we've had this discussion as we started today's class. Yeah, we need to multiply this by something that converts just this piece to minutes. So what do we need to multiply? Do we multiply by 60? Divide by 60? What do we do? Which conversion factor do we want? Do we do 60 minutes over 1 degree? Does that work? Okay. So let's do that. Everyone bust out the calculator. So we have 37 degrees and, wait for it, 40.425 times 60. Yeah, 25.5 minutes. Yeah? Did you get that? 25.5 minutes? So start, now, right now we have it in DM, right? In degrees minutes. So is it okay if I write it this way? Okay. Again, now we have 37 degrees, 25 minutes, and half a minute. Could you convert that, please, all the way now to seconds, this last piece? I think you don't even have to do this multiplication, but what will that be? What's half a minute in seconds? I think it's 30 seconds, and I haven't even finished writing. And so let's write this. Yeah, I don't need to type that one into my calculator, I don't think. So we can actually write it this way. We often just juxtapose those three numbers. 37 degrees, 25 minutes, 30 seconds. Okay? Let's do the next one. Here. All right, so down here, we're going the other way. I think I already know the answer. If it's in degrees, I know this is going to be like 42 point, thinking back to this example, I think my answer is going to be like 42 point something. Yeah? So, I think I have 42 degrees, plus, now I have like 24 minutes. Now how many degrees is 24 minutes? Again, I need to convert that, just that piece, to degrees, to an amount of degrees. Let's kill a side conversation for a second here. 24 minutes. How do we convert that to degrees? Are you raising your hand? Yes.
Well, I was saying, wouldn't it make more sense to start from the bottom up and to like convert the seconds back into
and then like add them to the minutes or something? Yeah, you could do that. Yeah, I'm going to do it in one move here, but yeah, do whatever works. Anything correct is fine. So, anything. Right, I mean, there are many methods here, absolutely. So I'm going to convert this to degrees. So what is it? 1 degree? No. 1 degree up top over 60 minutes. Okay. And while we're at it, let's also convert the 36 seconds. Hey guys, I think everyone's learning would be helped by you calming down a little bit. 36 seconds. I can convert that to minutes. I know how to do that. Yes? But that's not what I wanted. I want it in degrees. So can I do both of these at once? Cancel, 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 cancel. Right? I'm just going to type this all in right now. You do the same, please. 42 plus 24 divided by 60 plus 36 divided by 3600. Did you get what I got? 42.41. Did you get 42.41?
Yeah.
Okay, and what is that? Degrees, hopefully. Degrees? All that's in degrees now. Now, it actually says to do it in radians though, doesn't it? So go back to your warm up for a second and think about how do I do that again? Yeah, multiply that by, which one is it? Yeah, multiply by pi over 180, you'll get approximately 0.740. All right, and I'll show. Yeah, so one thing I'd like to say there too is that notice you could say rad at the end, like radians, but actually we often prefer to leave radians unitless, and the reason should be somewhat clear from the definition of radians. Do you remember the picture we had up here a minute ago? Right? We said the radian measure, theta, is 2 feet divided by 5 feet. What does it come out to be? Just 2/5. And notice that there are no units, right? Like necessarily, because of our definitions, arc length divided by radius, these things don't have units, do they? Right? So I just want to make sure, if you want to make it clear to someone that it's radians, you're welcome to write radians. But actually, technically, this is just like a ratio of two things that have the same units. So ratios in general in life, ratios do not have units. So, all right.
Oh, you don't need to be like that.
Why is, next question. Right here, I have for you, ready to go, here, I'll put it in a box even, a formula that gives the arc length. If you know the angle in radians, theta, and you know the radius, this gives a formula for measuring the arc length. Just stare at that for a second and tell me, in a second I'll ask someone to explain, why is this obvious? Like stare at it until it becomes completely obvious that this is true. Based on the things we've talked about already today, why is this like not something I should have to tell you actually? So in a second I'd like someone to raise their hand and explain why that's obvious. I mean, I didn't like prove it or anything. Uh-oh. Like, why is that? Does she want to share? Go ahead, Liz. Do you want to share? Wait, why is it obvious?
Because the angle is arc length over r. So
Yeah, if you divide both sides of r by this equation by r, you get the thing we already talked about today, don't you? Isn't the angle equal to s over r? Right, so this is just like us solving for s, the arc length s. We good on that? Okay, next question. Then let's try this. Find the arc length s, find s, where r is 10 inches and theta is 10 radians. Now, before we go actually and do this problem, are we allowed to talk about 10 radians? A circle only has like 6.28 radians in it, doesn't it? 1, 2, 3, 4, 5, 6.28, right? A circle only has 6.28 radians in it. How can we even talk about 10 radians? I can't come across an angle in the wild that measures 10 radians. It doesn't even work. What do we mean? Is 10 radians meaningful in some sense though? Can we talk? What does that mean? It's like you. Yeah. So now we're not talking about. We have to like expand. If we haven't already done this in our lives, we need to expand our notion of angles, don't we? This is not an angle you could find in the wild. It doesn't measure an angle. 10 radians does not measure an angle. It measures like a rotation amount, doesn't it? Almost, kind of. Which now I think I can recover my bearings. Now I think I understand. Okay. It's like an amount of times you go around a circle. So how far did you walk if you walked around a circle of 10 inches? A radius 10 inches, 10 radians. You went around more than once, but not quite more than twice, right? So how far did you go? What's the calculation? What do you get? You're an ant, maybe. I don't know. What do you get? Not all at once. What'd you get? Yeah, you get 100 what? Inches. And notice again that I didn't put the radians there. I didn't load them into the equation with units. Just to emphasize again why. Because otherwise, if you consider them to have units, then you get an answer of 100 inch radians.
What's an inch?
I don't know either. Yeah, okay. So, why does that intuitively make sense? Well, if you walk 1 radian around a circle of radius 10 inches, you've gone 10 inches. If you walk 2, you go 20 inches. If you go 3, you've gone 30 inches, etc. Right? How about this one? This time we're looking for the radius. I gave you S. You know theta. So I'll try and fill in the blanks here. I'm good at filling in blanks. Find the radius. It's currently unknown. Any snags along the way that you need to discuss with me? The fact that it's in degrees is a little bit of a problem, maybe, given the fact that. By the way, the reason this definition, this little formula we came up with in the box is so elegant. The only reason it's elegant at all is because, again, we're measuring in radians. Like, can we put one more point for radians, right? Over on the side on the scoreboard, okay? Yeah. The arc length formula, if you have theta measured in degrees, is like S equals R theta times pi over 180, right? It's not, right? Not nearly as nice. So I'm going to convert to radians right away here, right now, in this equation. Okay? What does that come out to be? Pi over 9? Okay. So what's R then? What's R? What is it? 9 over pi. 9 over pi. Did all the units go away except for feet? Is that the radius? So that's like a little bit less than 3, yeah? Right? A little less than 3 feet. Let's skip the Pac-Man problem, even though it looks fabulous, doesn't it? Doesn't that look good? I do like that problem, but and we're gonna skip this video too. We'll watch that video tomorrow too, I promise. But I want to make sure we have like a little bit of a discussion about the following formula. Okay, we're gonna talk about suddenly we're talking about speed and velocity. So V equals R omega is the letter there, and that's what this says. And I want you to just think of taking the last equation. That's an omega. It's like written like a curvy W kind of. I want you to think about taking the last equation, S equals R theta, and I want to think about you having this equation and dividing through by some unit of time, like dividing through by minutes or something. Then what do you get on the left? You get some distance. Isn't arc length the distance measured in feet or something? Divided by a time. What is a distance divided by a time? It's a speed, isn't it? Or a velocity? Whatever. We won't split hairs yet. R we're going to leave as R. But what happens when you divide an angle by a speed? And the answer is something maybe you haven't thought about before, but it's your angular speed. It's like how many radians you do per minute or whatever you divide it by.
Like when you're doing donuts.
What?
Like donuts, when you go in circles.
Yeah, okay, yeah, well, anytime if that's the thing you think of when you're thinking about rotating, then, yeah. So this is what a problem would feel like, and I'll actually demonstrate this in front of you in a second. But we do kind of have two velocities we maybe care about when we have rotating objects. We want to maybe keep track of how fast the thing is actually putting down distance on the ground. That's like the traditional linear velocity that you've thought about all your life. How fast is it actually going? But we also might want to keep track about what its angular speed is. How fast is it actually rotating? So here's an example of a question, and actually I'll demonstrate it for you right before your eyes here in a second. We have a particle moving around a circular path of radius 3 feet, so it's got a 3-foot radius and it's spinning around the center. And it's going at an angular rate, this is omega, of 2 radians every second. Now how fast, linear speed, how fast is it actually traveling on the ground? Well, apparently we can use this calculation, right? Should make sense. Just got time in it now, right? It's just got time in it now, but it's really the same problem we were doing a second ago. What's your linear speed? Well, again, it's just your radius times your angular speed. And again, that's not like, I'm going to write 2 per second. Is that okay? Instead of 2 radians per second. So that the units come out to be what? It's going to be 6
Feet per second?
feet per second. So, I mean, that's the answer to this question, but it still remains to be seen in your life. Like, what did we just do? Let me show you. Okay, so here's the center of rotation. If I'm going to walk 3 feet in a circle 3 feet around this, I think I can do that about, by the way, 3 feet is 3 blocks here. So I'm gonna walk, try and stay 3 blocks away from it, and I'm gonna try and walk 2 radians per second. 2 radians is like that, right? It's like about that much. So here we go. Ready? 1, 2, 3, 4, 5, 6, 7. So
Wow,
does
this is incredible.
that make sense? All right, now next question. So I was walking on the ground at about 6 feet per second, probably, right? What if I was only on a radius of 1 foot? How fast would I be going? Would I be going faster or slower? If I'm still going 2 radians per second, I actually have to walk. Actually, we can be more precise. How much slower?
3 times.
Yeah, the third is faster, 3 times slower, right? So I get to relax a little bit. It's only 2 every, it's a little bit slower. What if I went 10 feet away? Yeah. No, I can't do it, but you can imagine, like, I don't think I could even do it, right? I'd have to, like, run on top of this. All right, we will spend tomorrow and maybe the next day too saying more about this idea, because it's a big one. See you tomorrow. Did everyone get, oh sorry, hey guys, I think I forgot to mention at the beginning, I didn't give you an assignment sheet because the copier was broken this morning. This is homework 1 up here. You can either memorize it, or write it down, or take a picture. I will give you the assignment sheet tomorrow too.
I only finished like half of it. Yeah, nobody's gonna check it.
You got it.